By the end of this video, you will understand what is minimum spanning tree. Also, we'll go through the Kruskal's algorithm to create a minimum spanning tree from a weighted and directed graph. So to understand minimum spanning tree, we will directly dive into the problem, and from that problem itself we can understand the minimum spanning tree. So given a weighted and directed graph, we want to find a subtree of this graph which connects all the vertices. So this is the spanning tree. A subtree of graph which connects all the vertices is spanning tree, and it should have the least weight. That is, sum of all the weights of the edges should be the minimum. So every single edge will have a weight attached to it. So the sum of the weights of all the edges that we use to create a spanning tree should be minimum. This is called as minimum spanning tree. So if you look carefully, on the left hand side we have a graph. Actually we have a weighted undirected graph, and on the right hand side we have managed to create a spanning tree. So sum of all the weights of the edges here is the minimum among all the combinations. There are various combinations by using which we can create a spanning tree. We could have actually removed this 7, we could have actually ignored this particular 7, and we could have taken this 10, right? Here 10. But that would have resulted in more weight. That's why we took the 7. So if you look at this carefully, all the vertices are connected and sum of the weight of all the edges is minimum. So on the left hand side we have a weighted undirected graph, and on the right hand side we have a minimum spanning tree. I hope this is clear. We will look for the Kruskal's algorithm to create this minimum spanning tree. So the key observation regarding this minimum spanning tree that I want to highlight is this. There are various observations actually. This is the most important one. First, try to understand this portion. In a minimum spanning tree of a graph, see, this is the minimum spanning tree here, the maximum weight of an edge. So what is the maximum weight of an edge? Here it is 8. We have the maximum weight as 8. This weight is going to be the minimum possible among all the spanning trees. There are various spanning trees that you can create from the weighted undirected graph. So this is the spanning tree. This is also a spanning tree. This is also a spanning tree. This is also a spanning tree. But for the minimum spanning tree, which is this one, maximum weight of an edge, which is this one, maximum weight of an edge in the minimum spanning tree is 8. Now this 8 is going to be the minimum among all the spanning trees that you can create. See, so for this particular spanning tree, the maximum weight of an edge is 10. Let me write that as well. Maximum weight of an edge is 10. Here maximum weight of an edge is 15. Here maximum weight of an edge is also 8. And here the maximum weight of an edge is 8. Among all these values, 8 is the minimum, right? So by this key observation, you can never have a spanning tree whose maximum weight of an edge is actually less than the maximum weight of an edge of a minimum spanning tree. So what does it mean? That you can never create a spanning tree of this particular weighted undirected graph by selecting only edges strictly less than 8. Try to do it. Select the edges strictly less than 8. See, this is 2, 6, 2, 5 and 7. You cannot create a spanning tree by just selecting these edges, right? 4 will be left out. So this is the key observation here. In a minimum spanning tree, maximum weight of an edge will always be the minimum possible among all the spanning trees that you can create. We just took this as an example. You can actually take any other graph and validate this key observation, right? Now let's look at the Kruskal's algorithm. So these are the 3 steps that we are going to follow in a Kruskal's algorithm. So initially all the nodes, right, of the original graph are isolated from each other. So we have 1 here, we have 2 here, we have 5 and we have 6. All of them are actually isolated. Then what we will do? Now we are going to sort all the edges by weight in an ascending order. Then we will pick the edges one by one. If the end of the edges are actually not connected or not present in the same subtree, then we are actually going to take that edge and connect those two vertices. Let's try to understand this algorithm by this example. Let's say you have sorted all the edges in an ascending order. So this edge is going to be the first edge, this edge going to be the second, this has 8 and this has 9. So now we will process one by one. Let's first take the first edge, which is connecting 1 to 2. And what does our algorithm say? If the end of the current picked edge belong to different subtree, then we are going to actually combine it and select that edge. So I will write here, this is the cost that we have till now. It is 0, as of now it's nothing. Now let's check the end of the edges 1 and 2. Are they isolated or they belong to the same subtree? So they are not connected and they are not in the same subtree. So we need to take that edge and connect these 2 points, right? So let's take that edge. So we took that edge with weight 2. So our cost is 2 now. Let's take the next edge. Next edge is this one, 3 to 5. It also has a weight 2. If 3 and 5 are present in the same subtree, we will not do anything. If they are present in a different subtree, then we need to take this particular edge and connect 3 and 5. As of now, 3 and 5 are isolated and they are not connected. So we will select this particular edge and add it into our cost. So we are going to select this particular edge and we will add it into our cost. Then the third edge is this, connecting 1 to 3. Now if you look carefully, 1 and 3 are also present in a different subtrees, right? So we need to take this particular edge and connect 1 and 3. That's what we will do. We will take this particular edge with weight 5 and connect these two subtree. Our cost will increase by 5. Now let's take the fourth edge which has a weight 6, which is connecting 2 and 5. Now 2 and 5 are already part of the same subtree. See, this is the same subtree, right? They already are connected. You can travel from 2 to 5. So they already are connected. So once we encounter an edge whose end are already connected, they are already part of the same subtree, we will ignore it and we will not consider it. Now let's take the next edge, which is this particular edge, connecting 1 to 6. Now 1 and 6 are not connected. They are actually residing in a different subtree. So we'll take this particular edge and connect them together. Our cost will be increased by 7, right? Then let's take the next edge, which is this particular edge, connecting 3 to 4 and has a weight 8. Now if you look carefully, the vertex 4 and vertex 3 are actually part of different subtrees, right? They are not connected. Hence we are going to take this particular edge and connect 3 to 4 and our cost will be increased by 8. Now you can take any other edge. Let's take this particular edge, 6 to 4. If you observe carefully, 6 and 4 are actually already present in the same subtree. So we are not going to consider this particular edge. Take the next edge, which is 15, connecting 1 to 4. 1 and 4 are already part of the same subtree. So we are not going to take this particular edge as well. Look for this particular edge, 2 to 3. 2 and 3 are already part of the same subtree. So we are not going to consider this particular edge. Now we have managed to create a minimum spanning tree. And this is the cost that we have. This is the least cost by using which we can create a spanning tree. Hence this is a minimum spanning tree. I hope the algorithm is very clear. Let's go through the proof of correctness of this particular algorithm. Though by this example, this is very clear that it will work, but let's go through the proof of correctness as well. So Kruskal's algorithm is creating a minimum spanning tree. So first, let's try to understand how it is creating a spanning tree. Then we will look why it is able to create a minimum spanning tree. Let's try to understand why it is creating a spanning tree. See, what we are doing in the algorithm of an edge belong to different subtree, then only we are combining. Otherwise, we are not even considering that particular edge, right? So, if you look here carefully, we actually ignored this particular edge, connecting 2 to 5. Why? Because 2 and 5 are already connected. If you take this edge, it will create a cycle, right? So, Kruskal's algorithm actually avoid creating any type of cycle. Also, if you look carefully, we are processing every single edge. So, if the original graph is connected, the algorithm will eventually find an edge that will connect two isolated subtrees. What does that tell you? Every single vertex at the end will be connected one way or the other, and there will not be any particular cycle by this algorithm. So, we will end up having a tree. Rather, I would call we will end up having a spanning tree which will connect all the vertices and there will not be any particular cycle in it. Right? Now we have understood that it will create a spanning tree. But we need to understand why will it always create a minimum spanning tree. So let's try to understand this by an example. Let's say we have selected some edges and we already have some kind of a tree with us, right? And it is a time of processing an edge E. Let's say you have an edge here. Let's say you have an edge here which is E, which is connecting X to Y. Let's call this edge as E. And let's say you have node A, B, X, and here you have Y. All of them are actually connected already. So the main question here is that, are we going to consider this particular edge or not? Are we going to consider this particular edge for our minimum spanning tree or not? If you observe carefully, by taking this particular edge E into our existing tree, it will create a cycle, right? That's the first case that we are going to discuss. By taking an edge E, it will ultimately create a cycle. So let's take an edge E. For better understanding, let's take an edge E. So we took this particular edge E. Now it has created a cycle. But remember, we need to create a tree. A tree cannot have a cycle. So you have to remove at least one edge. Either you have to remove this edge or this or this or this. Let's say you are going to remove any edge. Let's call it as F. So let's say you are removing this edge. Let's call it as F. Removing this particular edge will actually increase our cost. Why? Because of cost F is less than cost of E. That means the weight of this particular edge F will always be less than the weight of this particular edge E. Why? Because remember, we have sorted all the edges in ascending order. In Kruskal's algorithm, we have already sorted the edges in ascending order. If we have already taken this edge F, if we have processed this particular edge F, that means the weight of edge F will less than weight of edge E. So if we remove this particular edge and if we take this particular edge, the cost will actually increase because cost of F is less than cost of E. So it will always be bad to take this particular edge. So if E is generating the cycle, we will never take it, no matter what. Why? Because we are processing the edges in ascending order. Taking this particular edge will create a cycle. So we have to remove an edge to get rid of this cycle. Which edge we should remove? We should remove the edge which has the highest cost. And our edge E will have the highest cost. Why? Because all the edges are already processed and we are processing all the edges in ascending order. This makes sense, right? So if edge E generates the cycle, we will never take it. Now what will happen if edge E doesn't generate a cycle? So let's say you have something like this. Here you have A, then you have B, and then you have Y. Now taking this particular edge E here, it is not going to generate a cycle. Cycle is not generated. So if cycle is not getting generated, we will always take this particular edge E. Why? There is always a possibility of encountering an edge F that can actually connect Y to this particular subtree. See, why are we taking this edge E? To connect Y to this particular subtree, right? This particular subtree. That's why we are taking this particular edge E. But there could be a possibility that there exists an edge F, it will manage to create a link through node C or something like that, right? There is always a possibility of having an edge F that can actually merge your node Y into this particular subtree. There is always a possibility. But taking that particular edge F will always result in more cost. Why? Because we are processing the edges in increasing order. So it's always better to take this particular edge E than taking this edge F who has more weight. Makes sense, right? This we are discussing if edge E doesn't create a cycle. So now condition is very simple. If it creates a cycle, we will not take it. If it doesn't create a cycle, we will take it. And that's what Kruskal's algorithm is doing, right? So this is the proof of correctness. It will create a spanning tree by preventing the cycles. Also, it will create a minimum spanning tree by processing the edges in ascending order of their weight. I hope this is clear. Now let's try to understand the basic implementation of a Kruskal's algorithm. Let's say you have all the edges here. This ID will tell us in which subtree our current node resides, right? Every single edge will have U, V, and it will have a weight. It is connecting to U to V with weight this, right? So this is what the structure of edge looks like. Initially, all of them are isolated. That means they have their own ID. None of them are actually connected. Now we'll sort all the edges in an ascending order by the weight. Now we'll process all the edges one by one. Remember, we process all the edges one by one, and if they belong to the different subtree, then we add their weight to the cost and then we unite the subtree. We will look for the time complexity later on, but let's try to go through the implementation and let's dry run it first. So initially we have 6 nodes and they all are isolated completely and they have all the IDs as their own. So they are belonging in their own set. Now let's process this particular edge. This is the smallest edge we have, right? And 1 and 2 are actually isolated as of now. Their IDs are different. So what we will do, we will merge them together and increase our cost. So our cost will be increased by 2, and we are actually going to merge this 1 and 2 by changing the ID of index 2, right? We are changing it to 1. So we have managed to merge 1 and 2. Both of them belong to the same ID. Then we will take this particular edge connecting 3 to 5. Again, 3 and 5, let me write here the index so that it is clear. So it's 1, this is 2, this is 3, this is 4, this is 5, and this is 6. As of now, 3 and 5 are belonging to two different subtrees. See, they have different IDs. So we will merge them together by increasing the cost by 2, and we will update the ID of node 5 to 3, right? Then the next edge is edge 5, which connect 1 to 3, and it has a weight 5. 1 and 3 actually belongs to two different subtrees, right? They have different IDs. See, ID we are using to identify which subtree they belong. Initially, they all belong to their own subtree. That means they are all isolated. Now, node 1 and 3 actually residing in different subtrees because they have different IDs. So we will merge them. So cost will be increased by 5. So while merging, we need to update the ID of all the elements that is present in a subtree of 3. So in subtree of 3, we have two different elements. You have this element and you have this element. Remember, ID of 5 has been updated to 3. See, this is what we are doing in this for loop. We are iterating over all n elements and we are checking ID of that particular node I is equal to the current ID, right? UID. Then we'll update it to the VID, that means the new ID. So we'll iterate through all the nodes and we'll update the ID. See, 3 we are going to update it to 1, and 5, for 5 we will also update it to 1. Now all the 4 vertices 1, 2, 3 and 5 has the same ID. If you can see, 1, 2, 3 and 5 are actually in the same subtree now. Now let's take the next edge, which is 6. 2 and 5 already has the same ID. So we are not going to take this one. So we'll ignore it because it will create a cycle and we don't want cycle. Then let's take this particular edge connecting 1 and 6, which is 7. So 6 has its own ID, which is 6 as of now, and 1 has ID 1. That means these two are residing in two different sets. So we need to take this particular edge and combine. We are going to take this particular edge 7 and we will update the ID of 6 to 1. After that, we have an edge that is 8, that has a weight 8, which connects 3 and 4. Now if you look carefully, 4 has ID 4 and 3 has ID 1. All these elements are belong to the same subtree now, and 4 is isolated as of now. So we need to take this particular edge 8. So cost will be increased by 8. ID of 4 will be updated to 1. Now the ID of all the 6 elements is 1. So we have a minimum spanning tree now. See, these are the edges ultimately we select. See, all the edges are connected and we have the minimum spanning tree. So if you look at the algorithm in time complexity wise, we are first sorting the edges. Let's say there are m edges and we are sorting the edges. So that will take time complexity of m log m. And if you look at this carefully, we are iterating through all the edges and then we are iterating through all the vertices to update the IDs, right? That will take m into n, or you can also write n into m as well, n into n. M can reach up to n square. So it's better to write m into n. Then why are we writing n into n? Because we are creating a tree, right? There could be maximum n-1 edges that we are actually going to process. So once those n-1 edges have been selected, then we can stop the algorithm. And whenever we are selecting, then only we are iterating through this for loop, right? So it will be like n-1 into n. For all the other edges, we are not actually iterating through this entire for loop. We are actually ignoring those edges, right? So this is the time complexity that we have here. M into log m and n into n, that is n square. So if you have already gone through a DSU lecture of mine, then you know that this particular section that we have here is nothing but find and union. So this is the find operation that we have here. What does find do? Find tells you who is the leader. And that's what we are doing here. We are actually checking whether two different nodes belong to the same leader or not, same tree or not. If they both have the same leader, that means they are in the same subtree. So we don't need to process that particular edge. So this is particularly a find operation that we have here. Also, if you look carefully, we are actually updating these IDs, and this ID actually resembles the parent array that we have in DSU. Here we are taking O of n time whenever we select an edge. But remember, in DSU, the union takes constant amount of time. So this is a find operation right here, and this is a union operation right here. We can actually replace this particular for loop by union and find, and that's what we have done here. See on the right hand side, code is exactly the same. First, we are initializing parent and size array, we are sorting it, and we are processing all the edges, right? How we are processing the edges? See, here we are using ID to check whether they belong to the same subtree or not. But that we can do here by using find operation, which works in O of one time. And if they don't belong to the same subtree, we can combine those two vertices using union algorithm, which actually takes O of one time. Here, the algorithm that we have, where we are actually updating the ID, is taking O of n time. That is creating this n square time complexity, right? But if you know, the union algorithm takes only O of one time. So we are sorting all the edges. That will take m log m. And we are processing all the edges. That will take only m, O of m, right? This is O of 1, this is O of 1, and this is also O of 1. These constant time operations only. All the union and find operation are just constant time operations. We are just iterating here. That's why it will take O of m time. And we are sorting all the edges. That's why it will take O of m log m. I hope this is clear. So the final time complexity that we have is actually O of m log m. But our sort operation will take m log m. Then why have we written m log n? Let's try to understand that. If you observe carefully, see, our m represents number of the edges. Number of the edges at max will be n square. I can write m log n squared. That means I can write 2 into m log n. That's why we have final time complexity as m log n. I hope this is clear. Remember, we are trying to master problem solving skill. Our objective is not to master Kruskal's algorithm. Our objective is not to master DSU. DSU, Kruskal's algorithm, and all the data structures that we have and all the algorithms we have, the purpose of learning those is to master the problem solving skills. So what do I mean by problem solving skill? Given set of tools, you should be able to solve a problem. Or at least you should be able to understand the set of tools that you have are not enough to solve that problem. See, DSU and Kruskal's algorithm are tools for us. And all the problem that we see, like this particular problem, right? See, this particular problem that we need to find the minimum spanning tree. All these problems will actually improve our tool utilization capacity, right? Tool utilization capacity. What are the tools that we have till now? We have DSU and we have Kruskal's algorithm, right? So always remember that we are trying to master problem solving skill. See, all of these can be done by AI as well. AI can easily give you the most optimized solution for this particular problem. But AI can also give you how much 2 plus 2 is, right? So it doesn't mean that we stop learning 2 plus 2. We are learning all these algorithms to improve our problem solving skill.